Well, hello and welcome YouTube. Mr. Robbins back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step one aside as we jump into section 4.3 in the Big Ideas Math Integrated Math 1 textbook, writing equations of parallel and perpendicular lines. Concepts we've probably talked about a few times. I've especially brought up parallel in some of the problem sets problems recently. I almost feel like they expected us to know what that meant. Maybe, maybe not, but we still got to do perpendicular lines as a result of that. To know these parallel and perpendicular lines, we're going to have to know slopes. So slope-intercept form, probably a bigger talk on this than standard form or point-slope form. I guess point-slope form uses slope as well, but I can see why slope-intercept form will be a greater need probably. Need I say more? I don't think so. I'm going to jump into this thing right here. Jump into the description section down below, and you can find the PDF of this thing. We are writing equations, not necessarily graphing them. So if there's graph paper that's need be, it'll be down here. Otherwise, if not, well, don't expect to graph. And find problems in their timestamps in the description section down below as well. I'm going to begin with the lecture portion. As a guy's rounding, second heading for third. Hold on, let's see what happens. He's safe. All right, let's go ahead and get started. That's College World Series, by the way. We're going to identify and write equations of parallel lines and perpendicular lines. Obviously, different kinds of lines. We have to know what they mean. Parallel, never intersecting. Perpendicular, intersecting at 90 degrees. And knowing their slopes is going to, or well, slope-intercept form, but knowing their slopes is the biggest portion of that to begin with. And use parallel and perpendicular lines in real-life problems. We'll see to what extent they need to do those. I don't know how often I've done perpendicular lines in real-life problems for these things, so I'm interested to see what they talk about. All right, let's start with parallel lines and slopes. And, these are the two core vocab things. Parallel lines and slopes. Two lines in the same plane that never intersect are parallel lines. To be in the same plane means that these two aren't in the same plane, right? Think three-dimensional. I'm going at you here, and this is going across there. These are called skew lines. Not parallel necessarily, but same plane on your piece of paper, on my computer screen, things like that. They never intersect, and lines by definition go forever. So you can't say, well, what about these two? Look where this one ended. No, they go forever, so we now imply that they keep going that way, and then boom. Anyway, two distinct non-vertical lines are parallel if and only if they have the same slope. And they mentioned non-vertical. I didn't know. Oh, okay, all vertical lines are parallel. I was going to say I didn't know they had something specific about vertical lines, because vertical lines should be parallel as well, and there they go. Okay. Determine which of the lines are parallel. Now, when we look at them visually, they may all look parallel, or to you, some may not. You go like, oh, they don't look it, or they do. Let's go based off mathematics. The visuals can be there for us to do things with, to find slopes, but don't just say, they look like they are, so sure. There are a lot of reasons why we can't assume things based on a drawing, okay? Try and not do that. So we want to look at lines A, B, and C and their respective slopes. Now, if they give you graphs, I'm going to count them. Like from line A, I'm going down 1 and over 1, 2, 3, 4, 5. So negative 1/5 is that number. Right there for line B, we're going down 1 over 1, 2, 3, 4. That's a negative 1/4. And then the C is down 1 over 1, 2, 3, 4, 5. And that's negative 1/5. So, as you can tell, first of all, I did get the same slopes as they did. But second of all, not all of these slopes are the same. Lines A and C, however, happen to have the same slopes. Therefore, they are parallel. This does mean that eventually line B is going to intersect with line A. I guess probably up this way. Line B eventually will hit line A like that. Line B will eventually hit line C, down there somewhere. Because it's not parallel to them. The negative 1/4 instead of negative 1/5 happens there. A and C, will never, ever, ever intersect, and they have to have the same sign. And I think this starts to point to why we need to reduce our fractions, because let's say, and I'm sure they're going to give us examples, but let's say for line C we had negative 2/10. Then you're sitting there like, oh, that's not the same as negative 1/5, but it is, right? Because it reduces to it. So anyway, lines A and C are parallel. Line B is not with those. Okay, second example, doing it, writing an equation of a parallel line. Write an equation of the line that passes through the point 5, negative 4, and is parallel to the line y equals 2x plus 3. Now, we don't need to graph this for this to happen, and it depends on which form you want to go with. And what excites me here is if you know we just came off point slope form, and they're actually showing you alternatively, guys, you can do this using point slope form. I've mentioned a couple times now, there's more than one way you can write an equation in slope-intercept form. One way is through point slope form, which is totally valid. Sometimes I'll do it. Another way, which I grew up doing a little more so, is using slope-intercept form to write it, but what you have to do is a substitution of values. So we're going to take a look at what that looks like right now. First, you find the slope of the parallel line. Now, given that you have this equation y equals 2x plus 3, that's in slope-intercept form, that means 2 is your slope. Not 2x, by the way, but just 2. If your slope here is 2, we should know that parallel lines have the same slope. Therefore, the slope of your equation should also be 2. Now, what I tend to do before, well, not before here, but in between this step and this step, I tend to write an equation that says, so far in my equation, what I know is it will look like y equals 2x plus b. Now, I don't know what b is yet, but here's kind of the insert of that equation. So that's what they do. They say y equals mx plus b, our m value is 2. And we need to find b, the y-intercept, to write the equation of the line. Or this is an equation of the, oh, well, they didn't really officially write point slope form, but this is also an equation of the line, y plus 4 equals 2 times x minus 5. When all said and done, they did substitute their values in. It's not in slope-intercept form, though, and I'll mention one of the benefits of actually using point slope-intercept form versus point slope form for this. Just give it a sec. Now, anyway, y equals 2x plus b, right? We have m, we need b. So what we're going to do is use a solution that we have, which is 5, negative 4. We're going to substitute this for x and this for y in our equation, solve for b in it, and then rewrite this equation with that new b value. So what did they do? They substituted 5 for x and negative 4 for y. The same 5 for x and negative 4 for y that we could use in point slope form to find this same b value of negative 14 that they find right here. 2 times 5 is 10. Subtract 10 from both sides. They're getting b equals negative 14. That means their new equation is y equals 2x minus 14. There it is. We got it. We're all done. So this equation y equals 2x minus 14 is parallel to y equals 2x plus 3. Why are they parallel? Two things need to happen. They need to have the same slope, and they need to be different lines. So if you're in slope-intercept form, here's the other benefit. If you're in slope-intercept form, how do I know these are uniquely two different lines? Because they have different y-intercepts. They have different y-intercepts. Point slope form, I may have written an equation here that passes through the point 5, negative 4, but I can't guarantee that it doesn't pass through 0, 3. So I just need to make sure that it does. That's why I kind of like slope-intercept form for that. Now they said, write an equation. So you can write any of them, I suppose, but as you can tell, you can get in slope-intercept form and get that. So here's a new way to get in slope-intercept form, guys. Substitute the x and y into there and solve for b, and insert that b into your equation. If b is negative 14, boom, we got it there. Okay, I'm going to move forward. Let's look at perpendicular lines. Now, perpendicular lines are lines that make 90-degree angles with these guys here. So, to be perpendicular, the slope needs to do something compared to the other slope you have. They need to be what are called opposite reciprocals. They say the phrase negative reciprocals. I'm used to stating opposite reciprocals. And opposite does mean a sign change. Now, one thing that I think opposite has benefit of over negative is negative doesn't mean make it negative. For them, negative means change the sign, which is what opposite means, right? Change the sign. So opposite reciprocals is what I'm going to say more often than negative. You know, just like how I say vertically compress more than vertically shrink, you know, things like that. Anyway, what does it mean to be an opposite reciprocal? Well, the opposite part means change the sign. Reciprocal, you've heard that phrase a lot from me before. It means flip the fraction. If your number wasn't a fraction to begin with, make it one. If your slope was 2, the opposite reciprocal is negative 1 over 2. The 1 over 2 is the flipping of the fraction because this is 2 over 1, and it's positive, and making it negative, taking the opposite, is that right there. So here's a slope, here's the opposite reciprocal. Guess what these slopes are? They're perpendicular to each other. They'll intersect at 90-degree angles, and that's actually almost exactly what they have here. Here's a slope of positive 1/2. Here's a slope of negative 2. Now, anywhere along here, wherever we draw it, will be perpendicular to it, but we're going to come up with a very specific equation. It needs to cross through a very specific point. So let's, and vertical lines are perpendicular to horizontal lines, which is a good thing to mention, because what is the opposite reciprocal of 0? Negative something over 0, right? Which is undefined. Don't worry about the negative part, but horizontal lines and vertical lines are perpendicular to each other. Almost better to just know that, but good to go. All right, let's identify parallel and perpendicular lines. Let's see this example. Determine which of the lines, if any, are parallel or perpendicular. No graph. This time they just give you equations. This equation is in slope-intercept form, y equals 4x plus 2. Therefore, we should know that this has a slope of 4. Now, you might want to write it as a fraction, 4 over 1, to remind yourself of when you flip it, what happens, and when you compare to others, that kind of thing. This is x plus 4y equals 3, not in slope-intercept form. Now, they do some work to get it. They say write the equations in slope-intercept form. For us to do that, we'd have to subtract x from both sides. And then we'd have to divide everything by 4. And I'll be honest, this part of the y-intercept matters none to me, except for it needs to be different from other y-intercepts when it comes to comparing parallel lines. You can't have the same line, otherwise it's not parallel. Anyway, it's better rewritten as negative 1/4 x, so therefore the slope of this guy is negative 1/4. So we have a slope of 4 over 1. We have a slope here of negative 1 over 4. I think that's something we can mention. And this is this is not yet in slope-intercept form. So to get this in slope-intercept form, we add 2x to both sides. And then we divide everything by negative 8. And notice that this needs a fraction reduction. Positive over negative is negative. 2/8 reduces to 1/4, so that's a negative 1/4. And then x minus 2 is right here. So there's this equation with a slope of negative 1/4. So what are we seeing here? Lines B and C are parallel to each other. They have the same slope in different y-intercepts, therefore they are parallel. Whereas line A has the opposite reciprocal slope of both lines B and C. So A is perpendicular to lines B and C. That's what they're stating there. And that's our conclusion that we make. If we get it in slope-intercept form, that'll get us to what we need for a conclusion. Here's another example, writing an equation of a perpendicular line. This is going to be more along the lines of that example 2, writing an equation of a parallel line. So write an equation of the line that passes through this point, this new x, y, and is perpendicular to the line y equals 1/2 x plus 3. This is no different than the parallel lines problem, with one exception. Once you have this equation in slope-intercept form, which it is, you're looking for the opposite reciprocal slope of 1/2, not having it be the same slope. If you remember the parallel lines one, we said, oh, if this has a slope of 1/2, then ours has to have a slope of 1/2. That would be true for parallel. Perpendicular, we want the opposite reciprocal slope. So the way you're going to see me write that is, hey, the slope of our line is 1/2, so the opposite reciprocal slope is negative 2 or negative 2 over 1. I'm probably going to write negative 2 in that case. This is the perpendicular symbol. It's like an upside down capital T. Kind of looks like two things that are perpendicular to each other. If you imagine, hey, this makes a right angle with that, that's the symbol. It's not my made up symbol. But that's the slope of the perpendicular line. So we're going to use a slope of negative 2. Otherwise, it's the same problem. Now, they, in the example, started with point slope form to make it happen to get into slope-intercept form. Remember, you can do either. By you can do either, I mean you can use either method to get in slope-intercept form. It looks like they want their final equation to be slope-intercept form. I'm fine with that. I'm going to go ahead and do that as well. Every so often, I'll revisit point slope form to show you, hey, you can get the same thing. Anyway, they get y equals negative 2x minus 5. So they get some particular b value here. And if you do it using that slope-intercept form format by substituting that for x and that for, and by the way, that's what we're doing, right? Negative 3 goes in for x, 1 goes in for y. Plug them in, solve for b, and insert. This becomes your equation. Boom, 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 right there. This is perpendicular, specifically to this line here, opposite reciprocal slope. And the negative 5, this doesn't actually have to be different from 3 this time. What if this was a plus 3? Well, then it wouldn't cross through this point, but let's say that it crossed through the point we wanted and it was a plus 3. Is that allowed? Yes, because these are two different lines. They just happen to intersect on the y-axis, I suppose. But this was a minus 5. This is the specific value that gets you to cross through this xy value here. We did this without a graph. I anticipate doing them without graphs. This is, writing equations. What did I want to mention beyond this? Something. I forget what I wanted to mention. Maybe it was just that last part there, but I'll leave that. Writing equations for real-life problems. I'm interested to see what they have to say about perpendicular. The position of a helicopter search and rescue crew is shown in the graph. The shortest flight path to the shoreline is one that is perpendicular to the shoreline. And by the way, that is I don't know if the word is theorem, but that is a math truth in and of itself. The shortest distance between any point and a line is the one that's perpendicular to it, right? What's the shortest? This thing in blue, this thing in green, or this thing in purple? Which one's the shortest? Well, I drew the green shortest, but this one in green, because it's the one that goes most dead on to it, it's the perpendicular one. So they're saying the helicopter's flying to shore, it should fly perpendicularly, boom, to it like that. Anyway, write an equation that represents this path. Okay, so it's not like a real world problem, right? Helicopters don't go, you got to fly in y equals 4/3 x minus 10 formation. It's not quite like that, right? Anyway, we'll see what they have here, what they want to mention. But you got to understand the problem. So what we understand is we got to be perpendicular to this line. Maybe we got to find out what the slope of this line is, so then we can make sure that we have the opposite reciprocal slope here. And I don't know if the visual will be a requirement of this, if the red is actually part of the original drawing or if this is them drawing it. But let's say that you needed to find the shortest slope and then find the opposite reciprocal slope of the helicopter, for the helicopter. And then it needs to go through this point at mile 14 with a height of 4, whatever they're talking about. So what is the shortest slope? Pick any 2 points and find its rise over run, or in this case, a fall over run. It looks like it goes down 2 and right 3. And that's what they have here of negative 2/3. So the helicopter slope is going to be positive 3/2. You've got to take negative 2/3 and take its opposite reciprocal, like this, equals positive 3/2. Flip the fraction, change the sign. Don't just flip the fraction. That's what a lot of people think of this. Now, does that mean the helicopter's going up 3 over 2? No, apparently it's going down 3 and over 2. But a negative over negative is still a positive. It's still on that positive slope. Anyway, substitute the 14 and the 4 here. They used point slope form, and then they're getting it over. That's fine. You know, it's an either or, but it looks like we're still using slope-intercept form as a whole. If they force point slope form on us, either as a method or as a final solution, I'll do it. I'm going to swap every so often and use some point slope form here, but I'm also going to show you the brand new slope-intercept form version. And there's the equation. It's a word problem, but it didn't really use... It wasn't really a word problem. They could have said the same thing minus a helicopter, and we would have been good. All right, so that's the end of the lecture portion. Let's jump into the vocabulary and core concept check. We have question number 1, complete the sentence. 2 distinct non-vertical lines that have the same slope are parallel. Now, they stated distinct. That's one of the things here, right? They can't be the same. Vertical lines are also parallel, but vertical lines don't have slopes. That's why they're being very specific about that. I would probably say it kind of almost the other way. I'd say like 2 unique lines that have the same slope are parallel, with the exception of vertical lines because they don't have slopes, but it's the same answer. Number 2 on vocabulary, 2 lines are perpendicular. The slope of one line is negative 5/7. What is the slope of the other line? Justify your answer. Well, you have to change the sign of this. So my justification is going to be take the opposite reciprocal. And this is how I'm going to abbreviate that phrasing, opposite reciprocal. The slope of this one, you change the sign to positive and you flip the fraction to 7/5. And that's the answer there. Okay, guys, we're going to go ahead and get to the problem set. I believe we have numbers 3 through 36 to do, so not too many in particular, but it depends on the overall work. So I'm going to go ahead and get started. Numbers 3 through 8, we're going to determine which of the lines, if any, are parallel and explain. Now, I stated this in the lecture as well, and it's probably something that you've heard from me before. We're not going to just look at them and say, yeah, they look parallel. We're going to have to do the calculations. Now, my calculations on slope can still be counted with my rise over run. For A, I'm going to count I'm rising 2 and running 3. So the slope of line A, and I forget if the book did it this way, but I'm going to say M sub A, is positive 2/3. Now the slope of line B has a rise, from here of up 2 and over 3. So that's the same thing as line A. Therefore, they are parallel, 2 over 3. And line C has a rise of 3 and a run of 1, 2, 3, 4, 5. So up 3 over 5. Whether it looks parallel or not is not of our concern. It's what it calculates to. So lines A and B are parallel. Line C is just its own thing, right? Now, it did state which of the lines, if any, are parallel. I do wonder if we're going to end up getting into some that are where none of them are parallel. That could be the case. Now, they said explain. My slopes are my explanation. Same slope is what we're looking for, right? Let's kind of like match those up. Boom, boom. Okay, number 4. The slope of line A, we're going down 5 and right 2. So negative 5 over 2. Line B, and its slope is down 4 and over 2. Now, what I want to do is reduce this fraction to negative 2. Negative 2 or negative 2 over 1. It's up to you. And C, we go down to right 1. And I think this is one of the things that we want to look for, right? It's down 2 over 1, which is also negative 2. That means B and C actually share the same slope. Reducing the fraction actually got us there. A has negative 5/2, around negative 2.5, not the same. So B and C are parallel for number 4. Now we go up to number 8, and these next 2 do not have graphs. Well, the next 4 don't, but the next 2 just show the ordered pairs, not the graphs themselves. So number 5, we have line A passing through -1, -2, and 1, 0. I'm just going to go straight into the slope calculation, though, if that's okay. So I'm still going to work on my, say, y2 minus y1 over x2 minus x1, which is +2 over +2, or 1. So line A is a slope of 1. Line B has a slope of, let's do 4 minus 2 on bottom. I always try to keep the bottom positive, so I'm looking at that. And then 2 minus -2. So here I have 4 over 2, which is 2. And then line C, we have 0 minus -1 on bottom, and then that means I have to go 2 minus 1 on top. So that's 1 over 1, which is 1. So A and C share the same slope, therefore they are parallel. B clearly does not. Couldn't you see by the graph? No, they don't have a graph. A and C are parallel. Sorry, that says A and C. Hopefully you can tell by all the other information we have on the problem. Number 6. Slope of line A. Let's try this one in our head from what we have. We're rising from 3 to 9. That is a rise of 6. We're running from -1 to +1. That's 1, 2. 6 over 2 is 3. Slope of line B. We're rising from 2 to 14. That's a rise of 2. We're running from -2 to -1. That is a slope of that's a run of +1. From -2 to -1 goes in the positive direction. So 2 over 1 is 2, not the same. And then C rises from 8 to 10, that's 2. From 3 to 6, that's 3, and we get 2/3. I mean, I wish I had the visual to confirm what I have, but none of these are the same. None of the lines are parallel. I'm just going to have to go based off of my hope that I'm calculating things the way that they're supposed to go, but that should be the rises and runs of those ones. They're all positive, but that means diddly when it comes to it. They have to be the same. All right, numbers 7 and 8. These actually have the equations. What I want to do from these is simply get them in slope-intercept form. Slope-intercept form. So for here, you know, they say line A, line B, etc. So I can, I'll just put a little A here and then we'll work on it. So 4y plus x equals 8. If I get y by itself, then I'll get it in slope-intercept form, and then the term multiplying by the x ultimately is going to represent my slope. See, you can't look at this and say the slope is 1. It's not going to be 1. There are times that you could luck out and it'll still stay that number, but that's not the point of this, right? The point of this is to get y by itself, make sure you're in that proper slope-intercept form, because that's the one that truly reveals your slope. -1x over 4 is -1/4 times x, and plus some 2. Okay, so this is your slope of line A, -1 over 4. Slope of line B, also got to get in slope-intercept form. If I subtract x from both sides here, then I'll divide both sides by 2. Like this. And this will get me y equals -1/2 x plus 2. So this has a slope of -1/2, not the same as A. Interestingly enough, they actually have the same y-intercept. So if it did have the same slope as A, then it would be the same equation, which means they couldn't be parallel. They have to be distinct lines. But even then, still not the same. Line C is 2y equals -3x plus 6. All I have to do here is divide by 2 to get to that last part. And this is a -3/2 slope plus 3. And so line C has a different slope as well. So just like the previous question, once again, it looks like none of these slopes, although all negative, none of these lines are parallel. None are parallel. That's my conclusion I'm getting at. Once you're in slope-intercept form, that's the result we're looking for. Lastly, number 8, we have line A doing its thing, and B and C. All right, number 8. A. We have 3y minus x equals 6. Let's add x to both sides. And divide everything by 3. X over 3, better written as 1/3 x. So we now have the slope of line A. Let me do this. I'm going to put it on this side, because I want to write on the other side. I kind of went way too far down the ordeal that I had last time. Slope of line A. Slope of line B, we can do 3y equals x plus 18. If I divide everything here by 3, I get y equals also 1/3 x, and this is plus 6. We do, once again, have to see that we have unique lines, and we do. So slope of line B is the same as slope of line A. We have two parallel lines thus far. Line C, I have 3y minus 2x equals 9. Now, maybe you can project things early on and tell yourself, well, whether these are the same or not. This time it's a 2x that's dividing by 3 instead of an x that's dividing by 3. That's probably telling for you that, well, if I'm dividing by the same number, but this, if I'm dividing, if I'm dividing by the same number, but the numerator is different, well, then they're probably not going to be, parallel. They're not going to be the same slope. So this slope of line C is 2/3, twice as much as the other two. This time A and B are the parallel ones. Never had all three be parallel. But we want to get into slope-intercept form to get that revelation. Okay, 9 through 12, we're going to write an equation of the line that passes through the given point and is parallel to the given line. Now, they did have something in example 2 for us to refer back to if we need to. And example 2 did reveal the brand new way that you can write an equation in slope-intercept form instead of getting it into point-slope form first. So I'm going to show you that. So we're passing through a point, -1, 3, and the equation is y equals 2x plus 2. So given that we're parallel, our slope needs to be the same. If our slope needs to be 2, because this one's slope is 2, then our equation is going to look like y equals 2x plus some b. Our goal is to find this b value by substituting. Now I remember what I wanted to state in the lecture. We want to substitute this for x and this for y. A mistake that some people sometimes make is because this number's on the left, they sometimes plug that in for y, and then they plug this number in for x. Be careful on which one's x and which one's y. So let's substitute these ones in down here. Let's make the equation now say, instead of y, let's make it say 3 equals 2 times -1 plus b. And now we're going to solve for b. See, the whole idea behind this is a solution to an equation on the line. So this should make the left side equal the right side. What value of b makes the left side equal the right side there? If I add 2 to both sides, I get a b value of 5. This means that my final equation will instead say y equals 2x plus 5. This equation is parallel by slope to this line here. And with the y-intercept of 5, you do enough up 2 over 1s, or I guess left 2 right 1s or whatever. Excuse me, left 2 right 1s, down 2 left 1s. You'll land at the point -1, 3. Without a graph. We figured that out. Number 10. Number 10, we have 1, 2, and y equals -5x plus 4. Now, this is already in slope-intercept form, as stated before. This has a slope of -5. Our equation needs to have a slope of -5. It should say y equals -5x. And what is that b value that we need? Well, we'll figure it out shortly. Now, what you could do is the same thing as before, which is take this x and y, substitute them into here, and we'll get 2 equals -5 times 1 plus b, or 2 equals -5 plus b, and add 5 to both sides, and we get a b value of 7. Now, don't finish here. We need to. Don't be done at this stage. We have to finish it by writing y equals -5x plus 7. Now, some people will say, wait, you bring the y and the x back? Yes, these were a temporary substitution of one of the infinite numbers of solutions that exists on this graph. We needed to use them to find the b value so we can write the equation for all of that infinite number of solutions that we have of those x's and y's on this line. So yes, you bring back the x and y. Now that's one way to do this problem. We could do what we've done in the past, which is write it in point slope form. I want to remind you what that looks like. And you still use this xy though, right? This is your x1 and your y1. So we could have alternatively done y minus y1 equals m, but this is what you use, m times x minus x1. Now, in some cases, guys, this is a valid answer. In fact, it is a valid answer. They said write an equation. This works. It's point slope form, right? You've used it. This is the same graph. They seem to be in a big thing on converting it to slope-intercept form, so we'll be the same. And keep in mind, you can write this in slope-intercept form. This is the only way that we learned previously, and to be honest, this is the only way I thought that the book was going to show. So anyway, you can add 2 to both sides. and you get this y equals negative 5x plus 7. You know what the book isn't seeming to do, though, because this would have been in section 4.1 on slope-intercept form. Yeah, we're doing parallel, and we'll do perpendicular to a line, but they never just said find the equation of a line with the slope of this passes through this. But use this method. Use the slope-intercept form method right here. We've only done it in point-slope form so far. So we'll have to see if we can go back to that. Maybe the quiz review, I can look at it with you guys and do that a whole bunch. So anyway, what was my point of this? We get the same equation out of point-slope form that we did out of slope-intercept form in writing it in slope-intercept form. Either method. I think most people would prefer this just because they like the form more. I think I prefer it. Not because I know the form more. I just prefer it. Number 11. Now, that being said, that's if you're required to write it in slope-intercept form. If I were allowed to write it in point-slope form, I would just write it there and I'd be done. All right, so this point here is 18, 2, our xy. This says 3y minus x equals negative 12. Now, if our goal is to write another equation here, and it didn't state the form, but we're going to say slope-intercept form, does this one need to be in slope-intercept form beforehand for that? Yes, because we need its slope. We need to find out what's parallel to it. So first thing I'm going to do here is get this in slope-intercept form, determine what its slope is, divide everything by 3, and you get y equals 1/3 x minus 4. Now you might have noticed, as I've stressed this importance more than I think really needs to be, but as you've noticed, this number doesn't really matter for what we're going to do, right? This may be the equation of our line that we're going to be parallel to, but then who cares what this y-intercept is? It can be a fraction, it can be, whatever. So don't spend a lot of time trying to compute whatever this is and making things with that. As long as ours isn't the same y-intercept, and I have no reason to believe that they will be here, maybe in later problems, don't worry about it. Our goal is to find the slope, and our slope that we need is the 1/3. So when we write our equation y equals mx plus b, it's going to say 1/3 x plus b. So you can tell this negative 4 meant nothing to me. As long as my answer won't be negative 4. My x is 18, my y is 2, so let's go back to that. Y is 2, x is 18. We take 1/3 of 18. 1/3 times 18 is 6. Oh, this is a b, by the way. I don't want you to think that's a 6. So equals 2. Subtract 6 from both sides, and you get b equals negative 4. That means our equation, using these two things, will be y equals 1/3 x minus 4. Oh! Guys, they're the same line. Okay. I didn't expect that, I was going to say. And when you compare it to this one, so guess what? We have the same line, which is pretty important to state. I wonder how they're going to write their conclusion and state it. These aren't distinct lines. When they said write an equation of the line that passes through the given point and is parallel to it, this is not possible. So not possible. If suddenly we've given ourselves reason to write this in slope-intercept form each time. If you notice, I had no way of determining, really in my head, and without a graph, I had no way of determining that the points 18 and 2 were the ones that would be the exact same line. Apparently, this one goes through 18 and 2. And if you take a look at it, 1/3 of 18 is 6, 6 minus 4 is 2. So it does go through there. So this is not possible. I don't know if that's the conclusion that we're supposed to state, but don't just box this. I did box it, but don't just box it and say, okay, we're good. Let's move on to the next question. This is actually, as much as I stated, this number doesn't really matter. It does. I was just saying don't spend time calculating it beyond the fact that you just need to make sure it's not the same as the other number. Well, these are the same. They're the same, so it's not possible. Two lines that are the same are not parallel to each other, and that's the point they're making here. So if I haven't yet led on to the fact that I do not do these problems beforehand, and I'm always caught on by surprise by what happens, let that be one of those indicators. All right, now number 12, I'm going to go ahead and actually revisit point slope form for this one just to show you again how that's done, even though we have this new method. But beforehand, I need to make sure to divide this thing by 2, get it into true slope-intercept form, so we get the true slope out from it. This is y equals 3/2 x plus 5, and yes, that plus 5 is so important to look at apparently. Now, given that this is a y equals 3/2 x, our slope that we're looking at is 3/2. We need to use this x and this y, I'm going to call it x1, y1, and I'm going to write this out in point slope form. So this will be y minus y1, y plus 5, equals m times x minus 2. That's an answer. I didn't yet get the answer, and I'd love to get it this time because I need to make sure that it's not the exact same, that I don't get the same y-intercept as this. So like I said, it's an answer. assuming it is truly parallel. Meaning it's truly distinct from the other line. 3/2 of -2 is -3, and I'm going to subtract 5 from both sides. Okay. So this y-intercept will be different from the other, given that they have the same slope. This is a -8. Here's the equation. There's the answer. And you do now see your two different methods that you can use to get that thing there. The alternative, I'll show it, but I'm going to go super fast on it. You substitute -5 for y and 2 for x. You get 3/2 times 2. Solve for b. 2/2 is 1. -5 equals 3 plus b. Subtract 3, you get b equals -8. And then you can write that into your equation there. Okay. That's the first 10 of this problem set from 3 through 12. Let's move on to numbers 13 and 14. Determine which of the lines, if any, are parallel or perpendicular. Explain. So parallel can still be in the cards, but perpendicular is also potentially in the cards. So red. Listen, red is never going to be parallel with either of these two. That doesn't matter. But will it be perpendicular with green and or blue? We'll find out. And if it's perpendicular with one and those other two are parallel, then it's technically perpendicular with the other, but we'll also see that. Now, line A is in blue. So I can see a rise of 3 and a run of 2. So the slope of line A is 3/2. The slope of line B is this one here. That's down 2 and right 1, 2, 3, 4. So the slope of line B is -2/4, which you must reduce, -1/2. Slope of line C goes from, or up 1, 2, 3, 4, 5, right 1, 2, 3. Up 5, right 3. They said which of the lines, if any, are parallel or perpendicular. They start off pretty strong by showing you that none of these are parallel or perpendicular. A and C are the ones that could have potentially been parallel. They're not the same. They're as reduced as can be. They're not the same. B is the one that could have been perpendicular to either. I was looking for a -2 slope, or a +2 slope, for either of these ones, and that's just not the case. So none are parallel or perpendicular. The parallel symbol is this, like two vertical lines there, and the perpendicular symbol I showed you before, perpendicular like that. So that's my conclusion. None. They might have looked at though too, right? You might have looked at the green and the red and said, "Yeah, look at that right angle there." Or the green and the blue. They look parallel to me, but apparently not. Number 14. A is in blue. And for A, I'm going down 1 and right 1, 2, 3. So -1/3. B is in red, down 1, right 3, -1/3. So C, if C is perpendicular to 1, it's also perpendicular to the other because they share the same slope. So let's check out C. C goes up 1, 2, 3, 4, 5, and right 1, 2. And I'm going from the points that they gave me, but that's up 5/2. -3/1's opposite reciprocal slope is 3. 5 divided by 2 is not 3, like 6/2 would have been. So C is not perpendicular to them. But these two are parallel. So it's interesting for the new section, or this new block of problems where they're introducing perpendicular. The first two questions, they haven't had it yet. In fact, they've had a parallel set. So this is like the same set as before. The first two graphs, next 2 points without graphs, the next 2 equations. The final 2 are equations. So for A, in this case here, the slope of line A, I should say. Let's do again, I can probably do some of these in my head. So I'm rising from 1 to 3. So that's 2. We're running from -2 to 0. That's 2. And it's +2. So you get a +1 on that. B, the slope of line B. We're rising from 1 to 4. That's 3. We're running from 4 to 6. That's 2. 3/2 does not reduce, so we'll leave it like that. So not parallel. C has a fall from 3 to 1. We go down 2, and then 1 to 4 is still our run. That's positive. We go right 3. Now, 1, being 2/2, is not any version of those, same or opposite reciprocal, but B and C are opposite reciprocals. This is positive, this is negative. The fractions flip. So B and C are perpendicular to each other. That's it, and that's all. Assuming, again, the calculations are all good. Number 16, and again, they're giving me numbers that are very helpful for me to not have to write the extra steps. Why write 13 minus 10 when I know that 13 minus 10 is 3? You know what I mean? And 4 minus 2 is 2. 13 minus 10 is 3. 4 minus 2 is 2. Give me the good numbers. Slope of line B, we're rising from 9 to 12. We're running from 4 to 6. Slope of line C, we're falling from 10 to 9. We're falling 1 from 10 to 9. And we run from 2 to 4 like that. Negative but not opposite reciprocal. It's opposite but not reciprocal of these two. And these two are parallel to each other. So lines A and B, once again, are parallel. Not enough perpendicular going on. Okay. Let's go to number 17. Once again, slope-intercept form is what you're going to want to get out of this. So I have, for line A, I have 4x minus 3y equals 2. Let's get y by itself. Subtract 4x from both sides. 2 minus 4x do not combine. And then we'll divide everything by negative 3. Now this is one of those instances where that fraction y-intercept is going to be a little in the way. But negative 4 over negative 3 is positive 4/3. So positive 4/3 x minus 2/3. Whatever, as long as I don't get the same thing as that, there's line A's equation. The slope is 4/3. Line B has the equation y equals 4/3 x plus 2. It's already in slope-intercept form. It has a slope of 4/3 as well. So you see two parallel ones. Line C, 4y plus 3x equals 4. We will subtract 3x from both sides and then divide everything by 4. Remember, as these 4's cancel, these 4's don't. They just become 1. They all become 1. We just don't write the 1 in this one. Negative 3/4 x plus 1. C has a slope of negative 3/4. All right, what do we have? A and B are parallel to each other. They both share the same slope. C is the opposite reciprocal of A and B, therefore perpendicular. So this time I'm going to type it out. Just a little bit more to say. So C, well, I'll say this. Line C is perpendicular to both lines A and B. Now, that actually creates the implication that A and B are parallel to each other. But I'll still state it, which are parallel to each other. Well, sort of. We need to make sure that we're indicating they're also unique, that they're distinct lines, that they're not the same line or something like that. So maybe I should put that. Okay. And then number 18, the last set from those. Hold on, I'm trying to box this. Okay, number 18, and I think that's the halfway mark. We go up to number 36. But we got to finish the problem first, right? Only halfway by problem amount, not by necessarily time. Line A is y equals 6x minus 2. We got a slope of 6. Let's see if we can just go based off our knowledge of that, right? Line B has 6y equals negative x. Y is not by itself. Now it is. And now that's negative 1/6 x. Okay? That's the slope of negative 1/6. C has y equals, well, what is it? Y plus 6 equals 1. 6x equals 1. And then we subtract 6x from both sides. And we get y equals negative 6x plus 1. All right, let's look at them. We got 6, not 6x, but we got 6, negative 1/6, and negative 6. 6 and negative 6 are not perpendicular to each other, nor are they parallel to each other. They're just opposite slopes. One is going up 6 over 1, one's going down 6 over 1. They intersect, not perpendicularly. However, this is an opposite reciprocal of that because 6 is 6 over 1. So 6 over 1, negative 1 over 6 means A and B are perpendicular to each other. C is just a nothing burger in comparison to them. So lines A and B are perpendicular. Okay. All right, through the halfway mark of problem sets of problems. Let's now write equations of lines through given points that are perpendicular to the given line. So this is just like this parallel stuff we did before. We just got to take the opposite reciprocal slope before we move forward. So number 19, we have 7, 10, And then this is the line y equals 1/2 x minus 9. So if this one has a slope of 1/2, its opposite reciprocal slope is what we need, which is -2. So the difference between, again, the problems was parallel. I'd use this slope and keep going, but perpendicular, I got to use this one. So as far as equation goes, remember this will be our x, y we substitute in the equation. Y equals -2x plus b. So we're going to do 10 equals -2 times 7 plus b. You know, I'm hoping for the, I don't know if they have error analysis questions. I'm hoping for the error analysis questions, they plug in 7 for x and 7 for y and 10 for x, because that is a common mistake that I see. Anyway, so -14 plus b, and we add 14 to both sides, and we get b equals 24. If b is 24, then that can go in with the equation here, y equals -2x plus 24. Keep in mind, y'all, that we do need the perpendicular line to this one. And it doesn't matter if the y-intercept is same or different. It can be what it is as long as it's perpendicular, and it technically it should theoretically cross through that point. Number 20, -4, -1. Are our x, y values. For this point, for this equation, y equals 4/3 x plus 6 that we will be perpendicular to. So this is a slope of 4/3. We need its opposite reciprocal slope, which is -3/4. So our equation is going to look like this funnel, y equals -3/4 x plus b. And we need to find the b that goes there by substituting this for x and this for y. -1 is -3/4 times -4 plus b. Negative times negative is positive. 4/4 is 1. You're just left with a 3. So -1 equals 3 plus b. Or b equals, if you subtract 3, b equals -4. So our equation will be y equals -3/4 x minus 4. Okay, numbers 21 and 22, not in slope-intercept form to begin with. For the sake of diversity, for number 21, I will go ahead and do this in point-slope form, and then rewrite it. I'll use point-slope form to write it in slope-intercept form. So we have -3, 3, but it doesn't change the fact that we still need the slope. So we're going to write this one in slope-intercept form by dividing everything by 2. We get y equals 4x minus 3. So this got a slope of 4. We need its opposite reciprocal slope. Remember, 4 means 4/1. So the slope of the opposite reciprocal is -1/4. So this time let's do this. Our x1 and y1 with our slope go here. Y minus y1 equals m times x minus x1. Try not lose sight of that one. Obviously, in our quiz review, we're going to do some point slope form things and, all that. But, let's not add 3 yet. But, this won't be fun no matter which way you did this, by the way. What was I going to say? Yeah, but you have two methods now. So, kind of pick and choose. So I got y minus 3 equals -1/4 x minus 3/4. And I need to add 3 to both sides. I need to add 3 to -3/4. So you might go like, Mr. Robinson, the one time you used point slope form, you got a weird fraction. We got to get a common denominator. I'm not going to use that again. You would have had to have done the same thing for slope-intercept form, fraction common denominator. This isn't a different answer than slope-intercept form. It's just a different approach. It's a different way that we come from it. I'm going to get a common denominator by multiplying 3/1 with 4/4. And now we're going to be doing y equals -1/4 x minus 3/4 plus 12/4. -3/4 plus 12/4 is 9/4, positive 9/4. And that's what we get. Now, understanding that we might get another fraction again, I don't know if we do or not, I'm going to go ahead and do this one in slope-intercept form. So I end up going, see, that's what happens. I don't know if we will or not. In fact, I don't think we will, looking at some of the numbers. No reason to get a fraction on this one. We get 8, 1. We have to go through 8, 1, but we do have to get y by itself. Subtract 4x. And divide everything by 2. Yeah, no reason for fractions here. So we get y equals -2x plus 6. So The opposite reciprocal slope, can we just go straight into it? I don't know. I feel like I still need to write it because I need the in-between as far as what we're doing. Slope is -2. The opposite reciprocal slope of this guy is positive 1 over 2 because it's -2 over 1. So we have that. So our equation is going to look like some sort of y equals 1/2 x plus b. Let's find the b. 1 for y, 8 for x. All for 1, 1 for all. Half of 8, not a fraction. Plus b. And subtract 4 from both sides. You get b equals -3. So our equation will be y equals 1/2 x minus 3. I only wish that we got to see these on graphs to confirm what that looks like, but I think enough's enough on that. Okay, in exercises 23 and 24, write an equation of the line that passes through the given point and is parallel and perpendicular to the given line. So we get to kind of do both of them. Well, not kind of, we do. So this line right here, parallel to it, we got to find that equation, and perpendicular to, we got to find that equation. The graph, using the graph to get the answer isn't really what we're trying to do, right? It's not like I want to use this to get the y-intercept, although I think through perpendicular, I'm going to predict it's a 1. But, you know, that's not kind of our goal here. Our goal is to kind of use this through other means. Now, here's what we need. The only thing from the original line we care about is the slope. Honestly, I don't even care about its y-intercept. How come? Because I know that this point isn't on that line, therefore it will be a distinct line. So the only thing I care about of the original graph right here is a slope of, what was that, -4? 1, 2, 3, 4. Slope of -4. So I don't even need the equation of the first line. I just need the slope of the original, and I need to go through, actually let's do this. On this, I'm going to say we have to go through the point 4, 3. Now this becomes new information, right? We revealed this. So here's the original slope. Now I will need to use the original slope for the parallel line. For the perpendicular line, I'm going to need the opposite reciprocal slope, which is positive 1/4. So we have two different equations to do with the same concept going on. In this one, I'm going to plug in this for y, this for x, and solve for b. In this one, I'm going to substitute 3 for y and 4 for x, and solve for b. mx plus b. Same thing, right? That's the whole goal. And I really like these problems for that. It just goes to show you, you're doing the same thing, just different slope. In this case, take opposite reciprocal. So 3 equals -16 plus b. Add 16 to both sides. And here you get a b value of 19. We'll see whether that looks like a good number or not. 1/4 of 4 is just 1. So 3 equals 1 plus b. And here you get a b value of 2. Now, did I expect... Wait, hold on a second. I thought I said I was going to expect a b value of 1. Oh, down... Oh, you know why? 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 Because I was looking at this as this is the slope that we need. And guess what? I couldn't even tell. That's not perpendicular. Right? I don't know if you can tell just by tilting your head that way. I was thinking, oh, I have to go through this point. You don't have to go through this point. You just got to go through the line perpendicularly. So the slope of 1/4 is perpendicular, and apparently it hits a y-intercept of 2. There we go. I realized something as I'm doing the problem. Anyway, I get a b value of 2. And so I got my two different equations. For the parallel one, I'm getting y equals, use this slope, -4x plus 19. And for the perpendicular one, I'm getting y equals 1/4 x plus 2. Two totally different equations, right? I see they're opposite reciprocals, but beyond that, there's no relationship between the y-intercepts of these two. Now, do I trust 19 as a y-intercept here? Probably. This would have gone pretty high up parallel to hit to 19. I'm going to believe that that's that for sure. Okay, number 24. Now, in number 24, they gave you no points on the original line, so we're going to have to just discover for ourselves, right? I see that it's crossing through this point right here, and I see that it's crossing through this point right here. So I'm seeing a slope of a rise of 3 and a run of 1. So the slope's going to be 3. First of all, we're going to go through 3, -2. Our slope, how did I write it? Our slope is 3. So our opposite reciprocal slope will be -1/3. Opposite negative, reciprocal, flippy, flippy. So our point is 3, negative 2. This time I'll use point slope form for both of them, okay? On point slope form, there's, for the parallel, this time I'll put parallel on top. Parallel and perp for perpendicular. So we divide them up. We have y minus y1 equals m times x minus x1. Here we'll have y minus y1 equals m times x minus x1. Same thing, but not. And listen, these could be answers. These could be answers and you'd be done. We're done. I won. I'm finished. No, let's just keep distributing. I mean, not no. Yeah, you could do that, but the book hasn't. I think of some other video or some other assignments where they do say write it in slope-intercept form. So let's do that. So y equals 3x minus 11 comes here. When I distribute negative 1/3 into these, at least negative 1/3 can go evenly into these. So negative 1/3 x, I mean, this doesn't matter if that's a fraction. But negative 1/3 times negative 3 is positive 1. And then I subtract 2 over on these guys and I get a negative 1. So those are the two equations. We're done. We got error analysis, folks. Number 25, describe and correct the error in writing an equation of the line that passes through 1, 3 and is parallel to the line y equals 1/4 x plus 2. So if we pull out the slope of 1/4, of this right here, the slope is 1/4. For parallel, we want to use 1/4. If you notice, they used a -4. So this kind of, generally they wouldn't do the opposite. Well, I shouldn't say that. I can think of times that they might do that. If they're like, I just learned how to do perpendicular lines, so I want to use that. So now they used point slope form to get the answer. That's fine. We just did it up here. They took the opposite reciprocal slope for a parallel line when they should use the same slope. Now, I'm going to assume everything else they did after that is right. Normally, it's just one mistake, and then we're done. And when I'm looking at it, that looks all correct. So we need to, though, write y minus 3, and that's correct. The 3 is the y value, and 1 is the x value. But not -4, we got to use 1/4. 1/4 times x minus 1. Now, they make us do the harder work because we are going to have to deal with a fraction on this minus 1/4 because we're going to add 3 to both sides. Now, 3 minus 1/4, 3 is 12/4, is the same as 12/4 minus 1/4. What is 12/4 minus 1/4? 11/4. So y equals 1/4 x plus 11/4. 11/4. Weirder answer, but the answer for slope-intercept form. Number 26, describe and correct the error in writing an equation that passes through and is perpendicular. Well, they attempted to work off this thing here, the 1/3, and they said, let's take the opposite reciprocal. But they just took the reciprocal. Their 1/3 turned into a 3. 3 never turned negative. If I have a slope of up 1 over 3 and a slope of up 3 over 1, are those perpendicular? Heck nah. I need one that's going to be down 3, right 1. That'll be perpendicular this way. And that's exactly what's needed here. Does this mistake happen? Yes, it does. Like I said, people get more focused on the reciprocal part flipping. They forget about the fact that the sign has to change as well. So, when finding the perpendicular slope, they only took the reciprocal and didn't change its sign. Everything else, again, assumed to be correct or proper from what they did. No other errors to look at for them. So let's fix what they have, though. Y minus -5, that's the right substitution. I'm going to write y plus 5, equals, and then for that slope of 1/3, if the slope is 1/3, the opposite reciprocal slope is -3 over 1, but negative, not positive. So -3 times the quantity x minus 4. Now when -3 distributes, we get y plus 5 equals -3x plus 12 instead of 3x minus 12. And subtracting this 5 over doesn't give you a -17. It gives you a positive 7. So y equals -3x plus 7. Okay. So they never did do one where they swapped x and y. They didn't even use slope-intercept form for either of these. They just went straight into point slope form. All right, 10 more questions in total. Number 27. A city water department is proposing the construction of a new water pipe as shown. The red one. The red one's the new one. The new pipe will be perpendicular to the old pipe. Write an equation that represents the new pipe. So, listen, word problem-wise, there's really nothing that's happening here. It's just, that's why I was saying, I can't think of word problems that I do that are perpendicular line things. This isn't a word problem. It is a word problem, but there's nothing we're doing based on its context. So the original blue, the existing water pipe has a rise of 4 and a run of 3. I'll kind of do this in its color. So the slope of that is 4 over 3. So for the red one, and I'll kind of do a darker red, the slope of the opposite reciprocal one is negative 3/4. And you could, I wonder if the drawing does that. Does it go negative 3/4? It does. If I see this point right here, I can tell it looks like it does do negative 3/4. Now, we want to get this y-intercept. You may assume that it's halfway in between. I don't know if you'd be right or not. I do know whether you'd be right or not. But let's not actually use the graph. I only use the graph to count slope, not to make my whole equation. So from here, I'm going to go back to our y equals mx plus b. So we are going to make an equation y equals negative 3/4 x plus b. Oh, hey guys, we need a point to go through. This one has the point 0, 3. I'm going to use, oh wait, no, I take it back. We need to use the point on the graph here. We have a point here, 2, 0. It's not the y-intercept, it's an x-intercept, but it does make y 0. And it does alleviate the fact that this will be a fraction. 2/4 reduces to 1/2, and negative 3 times 1/2 is negative 3/2. So b is going to equal positive 3/2. 3/2 is also 1.5. So I guess that number was between halfway between 1 and 2. But the equation will be y equals negative 3/4 x plus 3/2. And there's nothing we did differently here than before. There are no units for the water pipe or anything else. It's a word problem without really needing to do anything different. Number 28, modeling with mathematics. A Parks and Rec department is constructing a new bike path. That looks like train tracks, so we're going to have to do something here. The path will be parallel to the railroad tracks shown and pass through the parking area at the point 4, 5. Write an equation that represents the path. So to be parallel to this, we need to find the slope of the train tracks. Now we have points here at 8, 0 and 11, 4. So from 8 to 11 is a run of 3, and from 0 to 4 is a rise of 4. So up 4 over 3. I think the last one had a 4/3 slope, but we had to flip it. This one, we don't. How did I start it? So here, the original here, M, I'm not color coding, is 4/3, and we're going to use that. We want to go parallel to the parking area. I'm going to go ahead and use slope-intercept form again. So y equals 4/3 x plus b is our way to go. We're going to substitute 5 for y, 4 for x. So 5 for y, hold on, through 4. I'm having trouble writing. Through 4, 5. 5 for y, 4 for x. 4 times 4 is 16. You get 5 equals 16/3 plus b. As you can tell, slope-intercept form even sometimes has to deal with common denominators. Now here's the weird part of me writing this, minus 16/3, minus 16/3. I can write minus 16/3 outside here, that's fine, but then I have to put a plus 5. It looks a little iffy. And 5 is 15/3, right? Times 3 on top, times 3 on bottom. So there you go. Negative 16 plus 15 is negative 1/3, and that's our b value. So b is negative 1/3. Our equation should be y equals 4/3 x minus 1/3. 1/3 is a number between 0 and negative 1. Do I agree with that answer to be parallel to this thing? Let's see if that kind of does that scale like this. So I kind of draw a line right here, and let's just place it over here and see if it looks like it would hit negative 1/3 as a y-intercept if it's to scale. Yeah, that looks like it. I believe my answer. Looks good. Number 29. I have to sneeze, I think. Hold on. The vertices of a quadrilateral are 2, 2. Oh, we might have to use a... We don't have to use a graph, but using a graph might be a little better. The vertices of a quadrilateral are... Good, I didn't have to sneeze. 2, 2. 6, 4. 8, 10 for C. And for 8. Is it a parallelogram? Explain. Is it a rectangle? Explain. Okay, one reason I might like to use the graph, I mean, listen, there are a lot because I like to count slopes and things like that, but one reason I might want to use the graph is to make sure that the quadrilateral is in the order that I'm expecting, A, B, C, D, but I don't know for sure, so I kind of just want to plot them first. Here's A, here's B, here's C, 8, where's 8? 8, 10, and here's D at 4, 8. Okay, so listen, they probably didn't want us to use a graph. My point was actually to just look at whether or not these are going in that order so I know what to calculate. Okay. I'll do it off the graph first, sure, and I'll confirm another way that we were probably supposed to do it beyond this. Now, is it a rectangle? It doesn't look like it's going to be. But what would we check on these? Our goal is basically to find the slopes between these lines. I want to find the slope from line A to B, from line B to C, from line C to D, and from line A to D. Segments, from segments, but they're still the same as the lines. So, okay, I won't count them for the sake of graph stuff. I won't count them. I will calculate them. The slope of line AB, segment AB, is y2 minus y1 over x2 minus x1. It's a little long overdue that we haven't done that. That's 2 over 4, which is 1/2. The slope of line BC is y2 minus y1 over x2 minus x1. 10 minus 4 over 8 minus 6, which is 6 over 2, which is 3. The slope of line CD is 8 CD. Let's do 10 minus 8 over 8 minus 4. Keep them positive. That's 1/2. And the slope of line AD is 8 minus 2 over 4 minus 2. 8 minus 2 for y's, 4 minus 2 for x's. That's 6 over 2, which is 3. Okay, what are we looking for? They asked, is it a parallelogram? Is it a rectangle? So without doing anything else, just using these slopes. Part A, is it a parallelogram? Yes. Besides, it looks like it. No. It is a parallelogram. Oh, they called it ABCD. Duh. ABCD is a parallel, so I guess we didn't have to draw it at all. ABCD is a parallelogram because both pairs of opposite sides are parallel. How do I know they're parallel? We have two sets of same slopes that are opposite each other. So these two are parallel, same slope. These two are parallel, same slope. They're all positive, by the way. And we could have done accounting, but I'll leave it. So it is a parallelogram. That's what a parallelogram needs by definition. Part B. On part B, answering whether or not this is a rectangle is all dependent on right angles. Okay, rectangles have right angles. Does this? Well, not based off appearance, but it's really about the slopes. Okay, do the intersecting lines have opposite reciprocal slopes? In this case, 3, 1/2, not opposite reciprocals. So is it a rectangle? No. I mean, we could tell based off that appearance. But ABCD is not a rectangle because intersecting lines don't have opposite reciprocal slopes. Okay. That's it. Number 30, using structure. For what value of A are the graphs of 6y equals negative 2x plus 4 and 2y equals ax minus 5 parallel? And for what value are they perpendicular? So it's two different questions. Here's what I want to do. I want to solve for y in both equations. You know, find out what the slope is as far as I can. Divide by 6 here. And this becomes y equals negative 1/3 x plus 2/3. In the other equation, we have 2y equals ax minus 5. And if we divide those by 2, it becomes y equals a over 2x minus 5 over 2. So what we're doing is just comparing. Now, the 2/3 and negative 5 over 2 are different. So therefore, with parallel lines, we don't have any conflict of interest. But we're going to compare these two slopes here. When the original is negative 1/3, then when is it equal to a over 2, for what value of a? So let's start with that. Parallel. Parallel, for what value of a does negative 1 over 3 equal positive a over 2? If I multiply both sides by 2, that'll tell us. The a value needs to be negative 2/3. It's kind of a weird double check to figure out, so I'm just going to leave it as that. We can trust it. As far as perpendicular goes, the original slope here is negative 1/3, so the perpendicular one is positive 3 over 1. So for perpendicular, this one actually might be easier. Perpendicular, is that right? A over 2 needs to equal 3. Equal 3. So if I multiply both sides by 2 on that one, a is going to equal 6. So to be parallel, a needs to equal negative 2/3. To be perpendicular, a needs to equal 6. Okay. All right, let's go to number 31 on making an argument. A hockey puck leaves the blade of a hockey stick, bounces off a wall, and travels in a new direction. Your friend claims the path of the puck forms a right angle. Is your friend correct? Explain. Again, maybe visuals do or don't tell the whole story. That's not the point. The point is, can you calculate these slopes? So I have a line right here. These are scaled by 2s, by the way. So this is going up 4 and over 2. Oh, wait, they're scaled by 2s. So we're going up 8 and over 4. So up 8 over 4. Well, if they both go by 2s, it won't matter. 4 over 2 or 8 over 4. I'll call this line 1. Slope of line 1 is 8 over 4, which is 2. Call this one line 2. We're going up 8. And we're going 4, but 4 to the left. That makes it negative. Even if it was positive, that wouldn't be perpendicular. That would be parallel. Slope of line 2 is 8 over negative 4, which is negative 2. They have the opposite part down, but they don't have the reciprocal part down. So my friend is incorrect on this being a right angle, because the slopes are not reciprocals of each other. Although they are opposite of each other. So they have half of it done, right? Half the battle. Some people mess this up and think that these are perpendicular. Some people look at 2 and 1/2, think that they're perpendicular. You need both. 2 and negative 1/2, right? So this thing would have had to have gone up 1 over 2 or up 2 over 4 or whatever. It would have had to have gone in this direction here, and this would have been perpendicular with that. And then that wall wouldn't make any sense. But you know what I mean. It would have to be the angle. Number 32, how do you see it? A softball academy, charges students an initial registration fee plus a monthly fee. The graph shows the total amounts paid by 2 students over a 4-month period. The lines are parallel. Okay, they tell you they are. And they look so. Student B starts from maybe $75 and goes at some rate. I can't really tell. Student A is a little less than and goes at the same rate because they're parallel, right? Part A, where is it? Did one of the students pay a greater registration fee? Explain. Yeah, I kind of was just bringing that on. So number 32, part A, student B is paying a greater registration fee. They started, their y-intercept is higher, greater, larger? Pays a greater registration fee. What did I spell wrong? Registration fee. Because they have a greater y-intercept. Same word. Part B, did one of the students pay a greater monthly fee? Explain. No. They are parallel, and parallel means same slope, and same slope means same rate. No. They are, the slopes of the lines are parallel, the lines are parallel, which means the slopes are equal, or the same, are equal, which means the rates are the same. And that's the thing, right? I've brought up, I really didn't do any word problems with perpendicular lines before, and justifiably so when you saw the word problems we had to do. I've done them with parallel lines before, whether they intended on the things being, obviously they intended on them being parallel, but it wasn't necessarily a section on parallel lines. When two things start at different spots and they have the same rate, one will never intersect with the other. It'll never catch up. It's like if I'm older than you right now, I was born at this year, you were born at a later year, and we both age 1 year a year. That sounds dumb. And so I will always be older than you, right? I'll always be older than you. And you can argue that, oh, Mr. Robinson, what happens, if you die before me, then I'll catch up. If you die at 60, when I turn 60, I'll be your same age. Now, technically, I keep aging, right? The year now minus the year I was born. So, yeah, I'm always going to be older than you. You won't catch up to me in age unless we do an interstellar, different kind of rate, black hole kind of scenario. All right, in exercises 33 to 35, determine whether the statement is always, sometimes, or never true. Explain your reasoning. Two lines with positive slopes are perpendicular. Well, that's a never true case. So, never true. They need to be opposite reciprocals. And the opposite portion means signs need to be opposite. So both cannot be positive, both cannot be negative. Now, if you make a case where, well, Mr. Robinson, what if they're both positive if I did 0 and undefined? Because those aren't negative. Well, you're right, they're not negative, but 0 is not positive and undefined is not a number. 0 is neutral and undefined, right? And plus, they're talking about slopes, so we're not talking about those anyway. Number 34, a vertical line, undefined slope. A vertical line is parallel to the y-axis. Well, the y-axis is vertical. Vertical lines are always parallel to each other, but they have to be distinct. So what if the vertical line is the y-axis? This is a sometimes case. If the vertical line is on the y-axis, then it is not a distinct line, which is the exception to it always being parallel. So, sometimes cases are, when is it true? When is it not true? It's always true in every situation with this one exception. So that makes it a sometimes. Number 35, two lines with the same y-intercept are perpendicular. Well, that sounds weird. Well, here, if it said two lines with the same y-intercept are parallel, that would be never, because you can't, if they're parallel, then they're not distinct. Perpendicular, well, I think we saw an instance where they were perpendicular with the same y-intercept, but it says if they have the same y-intercept, then they are perpendicular. I mean, whether it says it one way or the other, it's a sometimes. Sometimes. I mean, the exception is, sometimes not. Sometimes they aren't parallel. For example, y equals 2x plus 3, and I need the same y-intercept, y equals negative 3x plus 3. Okay, they share the same y-intercept. They're not parallel. So, or they could be. It could be y equals 2x plus 3 and y equals negative 1/2 x plus 3. So sometimes yes, sometimes no. Okay, we got one more question. We have a thought-provoking one. You are designing a new logo for your math club. Your teacher asks you to include at least one pair of parallel lines and at least one pair of perpendicular lines. Sketch your logo in a coordinate plane. Okay, I have to attach the graph paper then. Sketch your logo in a coordinate plane. Write the equations of the parallel and perpendicular lines. All right, well, this is open-ended, so I'm going to do this copy-paste style. What should we make? I'm going to make the letter M for math. So let's do, oh, they have to be perpendicular. Okay, I'll make those parts perpendicular and those. Okay, I'll make a slanted version. So I want to make it kind of easy for myself. I'm going to start at this one here at negative 8, 0. Actually, that's a little long. Let's start at negative 4, 0, and let's end at 4, 0. I'm going to hit, let's rise 7 and run 1, and 7 and 1. So those will be parallel. So I'm going to have to come up with equations for those ones. And then I need to, and I'll use point slope form, I guess, for that. Now, I want to make these perpendicular. Let's just go down 1 over 1 like this, up 1 over 1. Okay, so let's go right here. Like that. So my ultimate appearance of my logo, I want to make look like this. It'll just be the letter M. I wonder if they wanted it to be a shape kind of thing. Gee, that doesn't look as cool as I thought it was going to look. I want it to look at this like M. Kind of like that, whatever. I guess that doesn't look very good either. Anyway, I'm just doing that, right? There's the logo. Actually, yeah, let's just do it like that, okay? So we have a couple lines. We have what's in blue. Mr. Robinson, nothing's in blue. I don't see anything. Oh, there it is. We have what's in blue there. I'll call that line A. I'll have green here. We shall call it line B. What did they say? Sketch your logo. Let's see. Ask you include at least one pair of parallel lines, at least one pair. Now, by the way, you could have had two lines that are parallel and then one that's perpendicular to the parallel. You know, things like that. I'm just going in my own direction with this. B, and then C and D will be these other two folks here. Let's do kind of a red. Not exactly a red, but that's okay. Actually, let's make it a little redder because my other one's going to be a purplish. So there. But I'll use darker red to write in. So C, and then this guy is going to be D. Purple. Purplish. Okay, now do not assume that my extension of these lines are what's needed, and also do not assume that that's a part of the logo. I'm just writing it like that so I have some stuff to go off of, okay? Just so you understand, those are the 4 lines that we're doing things with. Now, I do have ordered pairs that I want to use as well. So this is -4, 0. This is 4, 0. This is 5, 7. I forgot about this one. This is 1, 3, and this is -3, 7. Okay, so for line A, now here's what I'm going to do. I'm going to use point slope form for pretty much all of these. I would prefer doing that than slope intercept, actually. No, that's fine. I'll use slope intercept form. I'm good. So for line A, I have its slope as 7. Let me write all these. Slope of line A is 7. Slope of line B is 7. Those are parallel. Slope of line C and D. C is this one. That's a -1 slope. Slope of line D is +1. Okay? So these are opposite reciprocals. -1, +1. Flipping 1 over 1 still gives you 1 over 1, right? So these are 7s, etc. Okay. So for line A, I'm going to use the point -4, 0. So for line A, I have y equals 7x plus b going into -4, 0. And that'll be 0 equals 7 times -4 plus b. And it's -28 plus b. So add 28 to both sides. You get b equals 28. So A's equation will be y equals 7x plus 28. They said write the equations, right? So that's for A. Line B, it's y equals 7x plus b and crossing through 4, 0. Now, this is going to be a positive 28 instead. So 0 equals 28 plus b, subtract the 28 over, and you get b equals -28, right? So pretty much the same equation, except there. That was just happenstance because of how I wrote it. So these are the parallel ones. The perpendicular ones, you know, I could go off of, listen, I could go off the graph from this one, right? I think the point was to be inventive, and I think at this point I'm kind of running its course. So let's do this. We got this one based off the graph. This is hitting a y-intercept. Sorry. This is hitting a y-intercept here of 2 for D, and this is hitting a y-intercept of 4 for C. So C's equation, I'm going to do up here. C's equation is y equals -1x plus 4, and D's equation is y equals +1x plus 2. These are the perpendicular ones. Oh, wait. YC, YD. Perpendicular. Okay. Of course, you could have plugged in values and gotten the things in, but all that's going to work out. So, guys, I'm going to leave it at that. I know that I kind of cheapened out there. Thought-provoking means open-ended means you should come up with your own as well, but you do the same substitution that I do here. Plug in x, y's, come up with your equation once you have your slope. Guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. Coming up next is the sections 4.1 to 4.3 quiz. We've done a lot of writing equations in slope-intercept form, point-slope form, and we've used them here for parallel and perpendicular lines. A lot more slope-intercept form ultimately. We'll see what the review has in store for us. Thank you so much. Take care. I'm going to see you.